Good. So hello, everyone. Welcome back. So I'm Benoît, and I will tell you a bit how you can use interval and the guaranteed execution to actually find roots of functions in a guaranteed way as well. So to be sure to find all roots if there are some, and to be sure to know where they are. So the thing is start quite easily. You need to start with what is called a fixed point problem. That is, you need to start with a problem of the form. You have a box. In arithmetic, we can use both interval in one dimension or boxes in multi-dimension. Here, typically we have a box, and we search some point in that box such that some function psi of this point is equal to itself. So something that do not move when you're using this function. And to look at how we can approach that kind of problem, we first look at the image of our box. In principle, it's something strange, something we don't know exactly what it is. But what interval arithmetic provides us is what we call an extension. So it's a bounding box for it. So another box that is bounding it. And really, in practice, that's all we have. And then the smart thing we can do is we can look at how it compares to the original set we started with. And since we're looking at something that did not move through the operation of the function, we know that all solutions must be in the intersection, because everything that it is outside must have moved somewhere else. So we know all solutions are there, which is valuable information. And especially it gives rise to two very interesting configurations. And the first one is when the two are disjoint, because when the two are disjoint, there's no intersection. That means there is no solution. We have just proven that our fixed point problem has no solution, and we can end up there and be happy about that. And the other interesting things is, so there's no solution. Yes, no solution can exist there. And the other half of it is when actually the image contracts into X. Because when we have a contraction, we can use what is called the fixed point theorem. And the fixed point theorem tells us that if it contracts, there must be a solution of the equation provided that psi is continuous. And now the idea of interval root finding is quite straightforward. It is, well, just go through your interval until you find one of these two configurations. So in practice, it looks something like that. You start with some interval and you look at the image and you say, okay, the image is intersecting. That's bad. We cannot say anything about that. We don't know if there's a solution or not. But what we can do is we can say, well, let's just cut the interval into two and look at each of the half individually. That's exactly what we do in the package. And so next we go to look at one of them. Again, we look at the image, and here we can say, oh, good. There is no intersection. That means there is no solution. We don't need to get further. We know everything we need to know about this half of the box we started with. And then we just go through every leaf of the tree. Here, for example, looking at the image, maybe we find again, there is an intersection. We don't know what to say about it. And we go further and look at each of them separately until we find at some point, hopefully, that something contracts. In this case, we know, okay, there is a solution, there must be one. And here we can just refine the solution, which means iterate the fixed point iteration until it's either stop contracting or we reach some tolerance. And then we, as I say, we want to go through each of the leaves. And here we will, for example, see there is, okay, no solution again. And we are done because we have gone through all of the intervals. So for every region of the intervals, we know that either there is solutions or none. And that's really the core idea behind the package interval root finding. And I see there is a comment or a question. Yes, exactly, David. We know that everything is in this intersection in principle, so we would really only bisect that, but it makes more complicated animations. So here it's a bit of simplification for clarity. We could, from the first step, we could already say, okay, we know there is nothing in the upper half. Very good point. And then now you may. Yeah?
That's actually what the package does, right?
Yeah, it's exactly. I actually had to go verify because I was not sure if we did it, but we actually do it, yes.
Good.
And then you may ask yourself, because I told you a bit about fixed point problems. What do you do if your problem is not a fixed point problem? And we have something that is called a contractor. I think it's different to what was presented by David earlier, or in another talk about contractor for constraints. But the idea is, again, quite simple. We have this problem. We want to find x, such as f of x is 0. And what we have, if we have these funny contractors, they are functional of f and its derivative. And we can guarantee under some conditions that if f of x is 0, then it's a fixed point of the contractor. And then we can use what I just showed you and find the solution the exact same way. In the interval, we implement two different contractors. One is called Newton, one is called Krochik. And they are very similar. They have some different property, but it's generally not very clear. In general, they will give the exact same results, and they have the same rate of convergence, for example. One very neat thing about them as well, a property they share, is that since we are using derivatives, due to some other considerations, as a bonus, freely, that's for free, we know that if we find a solution, it is unique. If we have actually a strict contraction, the solution must be unique. So we can actually say either there is no solution or there is a unique solution is interval. And just to give you a feeling about how all of that work, I just wanted to have a brief showcase of how you can attack a problem such as that one. So I chose this function because it has its sinus of 1 over x. So it has a singularity with infinite many solutions at 0. So you know that whatever root finding algorithm you are using, you will miss some of the solution because there is an infinite number of it. But it's interesting to see what interval root finding can tell us about it. So let me go to my actual Julia script. And first there is some loading the function, and of course we can put the function. And I'm a bit surprised because I precompiled it. Yes, and it looks like that, so a bit crazy near 0, and otherwise just increasing. And actually what you may see is that for any number bigger than 0, there is actually no solution. And we can very easily use interval root finding and its root function to verify that. So here I'm asking for the root of the function f between 0 and 1. And what it gives us is a vector of roots. And if of these roots contain two things, one interval, saying, well, what we are talking about, and the status of this interval. And the status can either be unknown or unique. And you may notice that for all part of the interval that are empty, we do not actually return them. It's simply to save memory. That way, because we know they are empty, there's literally nothing more we can do with them. So we just discard them. And it avoids having thousands of useless intervals. But we know that if there is a solution, it's in this interval. And we'll never actually be able to prove whether there is a solution at 0 or not because there is a singularity. So it's pretty good. Now, for the left part of 0, here where things go a bit crazy, I want to show you something a bit more advanced we can do with the package. Namely, I show you that we are building kind of a tree, bisecting and bisecting and bisecting. We are building kind of a tree of the execution. And we can actually go and look at the tree during the execution or examine it whenever you want. And to do that is the next part. So I will need to use the derivative of the function to define the constructor explicitly. And I use forward diff just because I'm a bit lazy. I didn't want to write explicitly the derivative of the function. And then we can define what is a search object. And it's simply describing, it doesn't do anything by itself, but it's describing what search we're wanting to do. So we need an interval where to search the solution, a contractor, and some tolerance. And then it works like an iterator, so we can simply iterate over it as we do it. And at each iteration, the state is actually the tree of that we're constructing. And here, since it's a simple example, I don't do anything crazy. I just say, let's look at how many leaves we have in the tree, and if we have more than some threshold, save the tree in a global variables, so we can access it outside of the loop, and stop. And then, so we have a tree, which has a tree structure, very nice, which has a lot of elements because we went up to 10,000 leaves. And it's, again, we discard everything that is empty, and we have some in the leaves, some things, some are unique, some are unknown, some would need to be processed further to decide whether they are or not a zero. And then with some utility function, we can look at all the data, so only the roots, and most of them are actually unknown, unknown status. And here I just want to separate the new unique roots. There is like 800 of them, of the unknown roots, just to be able to plot them now. So first, what I do here is I take the middle of each interval and I plot a green dot for each of them. So here, each green dot is a root, single root that is proven to be there and proven to be unique. So you can be absolutely certain that for each of these dots, there is a unique root. And that's cool. And you see that it goes for some time near zero. And a natural question you can ask is then, well, until which point are we sure we have gotten all roots? Because we know at some point it will break. And to do that, I will just plot in orange and zoom a little bit the hull of the interval that are unknown. And it gives us something like that. So in orange here, we have the interval where things are unknown. Maybe there is some root. Maybe we got all of them, maybe not. And where first, maybe you notice that the function is going crazy again is because there is a singularity at zero. But here we can say, and it's, I think, kind of unique to root finding with interval, we can say that up to this value here, we got all roots. That's sure. And afterwards, we got some roots, but maybe not all of them. And that's kind of one of the, I think, a nice application of the interval root finding, saying that, well, we know what we are missing, really. We know that if we are missing in this interval. So yeah, that's basically what I wanted to show. To conclude, I have one more slide, which is basically about what we could add or improve still in the package. And one thing that kind of need love is that I believe we need a better interface for the rules function and the search iterator, because it's currently not on pair with other kind of solver you can find in the Julia ecosystem. If you look, for example, at the differential equation package, that is crazy, or others, we don't have as many options. We cannot have callbacks. We do not have an easy way to have maximum number of iterations, things like that. Another problem that have been discussed in other talks as well is that since essentially we are doing a brute force search, we are suffering very heavily from the curse on dimensionality. So something that could alleviate it a bit is to do smarter bisection in high dimension. Currently, we just bisect the biggest direction. In some cases, it's smart. In some cases, it's a terrible choice. And of course, there are those possible extensions, something a bit more fun that we can think about. And the two I put here is actually something I used during my master's thesis some years ago. And one of them is that we don't really have a nice interface. If you start with a fixed point problem, we don't have a nice interface for you to actually solve it without going through our contractors. And that's a bit of a shame, because sometimes your problem naturally contracts. And in this case, there is really no reason to do something crazy. And then another thing is that we can actually use function with interval parameters, and that give you information about a range of function. You could say all function in this range actually have a single solution in this interval. But we don't really have a clear support for them right now. And yeah, that's all I had for you today. Thanks a lot for your attention. And if you have any question, I guess you are welcome.
Thank you very much for the talk, Benoît. Do you have any questions?
Yeah, I have a question. Excuse me, I have a question. Yeah, very nice presentation. And yeah, so Benoît was one of the people who just arrived from the internet and started working on this package and did a really great job changing it in a very nice way to add this tree search and all of that stuff, and just keep track of all the bugs and things. So thanks a lot, Benoît. That was great. Yeah, I do.
Maybe if I can just ask a bit of context of that, I actually did it because I needed it for my work.
Right.
So I guess that's something quite common.
Yeah,
people should not be afraid if something is missing to just start to tinker with things.
Yeah, definitely. Yeah. Yeah, I was just going to say, so I think I've found I feel like there's some performance hit actually from the tree searching stuff. I've compared it to like a simple implementation, where you just have the basic Newton search and just really brute force bisection. And I think that's faster, but I haven't looked at it in enough detail to really be able to, I didn't file an issue or anything just because I haven't looked.
Yeah, I mean, I wanted to go back to it at some point as well, because for this talk, I look at it again, and I think I've become a wiser developer now. Right. There are definitely a lot of things I would do differently.
Yeah. I mean, if I look at the interval arithmetic code, we've actually rewritten it 2 or 3 times, basically from scratch. But now I would, write things differently, and yeah, definitely. Another comment I had is that you can't. So Newton and Kravchik, they are actually contractors in the same sense that I was talking about. So, Newton, if you you pass in an x and you calculate Newton of x intersect x, that is now a contracted box that it still is guaranteed to contain the root, right? So it's like a contractor for f of x equals 0 for that particular case. But yes, I was interested about what you mentioned about interval parameters, because I think if you have interval parameters, so you have a function that's like f of x equals sort of the interval 3 to 4 multiplied by x or something, then it's not so obvious to me how to use Newton to prove that there's a unique fixed point for each of those functions, right?
Yeah, it's in what I use it for. It sometimes works, sometimes not, because sometimes you do not contract enough to be in the interior. Okay. So you just keep being on the bound. So there is solution, but they may not be unique.
Right.
And what I did is not, when I used it, it was not the typical things, because my function went to 2 dimension to 1. So there was some, because normally all that go to stay in the same dimension. So I had to do a bit of adaptation left and right. But I think in theory, I think it works, because you just get everything included in the right way to have the fixed point theorem and all other things.
Okay. I don't know if anybody else has a question, or there's just one more comment is that, yeah, as I mentioned, you were saying that in high dimensions in particular, we are basically just doing bisection. But if you actually add in this kind of contractor constraint programming approach, then that should actually help you to remove big pieces of the set.
Yes,
in a different way from Newton.
But I believe, again, for some solution, before you bisect, the contractor is the whole set. So until you hit the point where you actually start, contractor start contracting, actually, it can eat most of the computing time.
Okay, thanks a lot.
Because, for example, if I can very quickly here, even here you see that, let's just close it. Very fast, we hit a very high number of intervals that are where we can simply not conclude anything, even so they're already contracted. Yeah.
Right, but in high dimensions, the difficulty is that you have such a big space to explore. And so
I mean, that's what makes things worse.
Sorry?
Yeah, I mean, I think they both help each other to make the matter worse.
So what I meant was, if you apply these in constraint programming methods, it's different from Newton, and it may be able to remove some pieces of the search space much more quickly. So you need to combine both of them. But the problem before was that it was difficult because there wasn't a good interface to constraint programming stuff, and now there is. So I think now it's going to be much easier to just use that sort of off the shelf to help with this package, maybe.
Maybe.